Joining us today, we have Patrick Taylor. Patrick is a climate scientist from NASA Langley. So welcome, Patrick.
Thanks for having me.
We appreciate you taking the time to meet with us virtually here and kind of to share some of the things that you've been doing and working on there at NASA. So,
Well, thanks for the opportunity. I'm really excited to share some of my science.
well, Sarah and I met you in person there at NASA Langley not too long ago, and everyone was very impressed with the talk you gave there and about the research you were doing. And we used that stuff in all kinds of lessons since then. The stuff that you let us use, your PowerPoint things and slides, and
Yeah.
we've hopefully enlightened hundreds of students there using your stuff. We appreciated that.
Yeah, no problem. I'm excited that other folks can use some of those things because they're out there for the world to use and to educate on how the climate's changing and particularly how the Arctic is changing.
And that's kind of the first thing I wanted to jump into is we say climate scientist, and I did not know years ago that when someone says climate scientist, that could mean a lot of different things. So many research areas that fall into climate itself. You could be specialized in just totally different things as someone else. And so you in particular, would you kind of explain what you specialize in and how that impacts the climate?
Yeah, so the climate system is really, in all sense of the word, it's truly a system. It's very interconnected. When you step back and start to think about, well, how do we predict and project how the climate system is going to change, you really have to consider the atmosphere, the ocean, the land, the plants, animals, and humans all kind of interact in this system. And so really it takes a true full system perspective to understand. As any one person, it's hard to really grasp all of those different components because they all have their various complexities. So my focus has been particularly in clouds and how clouds influence the energy balance of our planet, both at the top of the atmosphere, but also then at the surface. And the surface part aspect of that is really important when it comes to Arctic climate change and sea ice in particular, because that's where clouds can have a really big impact on whether sea ice freezes or melts and how it changes going forward. So really, I guess to put it most simply is the research I focus on is understanding how energy flows around the planet. As we can understand better how energy flows around the planet, then we can better understand our climate and then make better predictions and understand how it's going to change in the future.
Ooh. Now, one thing you said, just to clarify what you mean by, you said the top of the atmosphere.
Yeah.
What do you mean by the top of the atmosphere?
So the top of the atmosphere is not really like a hard defined kind of area or lid, but just somewhere very far up high in the atmosphere beyond several hundred kilometers, there's a place where we generally define that as the top of the atmosphere, and that's where you can where the change in energy, the amount of energy that's coming in from the sun and going out from the earth is essentially just balanced by just affected by those two factors, right? So if we're near the surface, there are a lot of other processes that are going on, like the wind's blowing, so there's kinetic energy in the air, there's potential energy that's in the temperature of the molecules and the water vapor in the atmosphere, and there are other exchanges that are happening of energy. We call them turbulent energy exchanges between the surface and the atmosphere. But once you get high enough, you're at the top of the atmosphere, really it's only those radiative energies that matter. So the sunlight coming from the sunlight, the energy from the sun, and then the amount of emitted radiation from the earth. So that's kind of it's kind of it's a fuzzy kind of definition for the top of the atmosphere.
Now, when we talk about energy and stuff, we're always, I mean, it's pretty common and understood that energy is coming in and coming from the sun. And we start teaching that in first grade, where the sun warms you up and things. But when you say energy emitted from the earth,
Yeah.
we don't as commonly think about that the Earth is. How is energy being? How are we losing energy as a planet?
So this can get complicated very quickly, so I'll try to um, stay. So anything that has a temperature emits radiation or radiative energy, right? So you and me, if we are all in a room together, when we're all allowed to be in a room together again, the body heat from all the individuals, the emitted energy from all the individuals in that room is essentially causing the body heat to warm up that room, right? And so this is where everybody who has a temperature is actually emitting radiation. It's not radiation like the sun, right? So the sun is very, very hot, and so it emits radiation in wavelengths that we can see, right? Visible light. And that's because it has a very high temperature. Whereas our body temperature, 98.6, is much, much cooler than the sun. And so it's emitting radiation, radiative energy at smaller wavelengths, or sorry, longer wavelengths, but those wavelengths that aren't visible. So we can't see it, but we can definitely feel it. And we feel it and we call it heat, right? And so just like our body heat and in a room, if we shove a lot of us into a room, the Earth also has a temperature. The surface has a temperature all around the Earth. The atmosphere has a temperature, and so all of those different surfaces and the air, the matter, is all emitting energy as well. And so while that energy is emitted in all directions, it's emitted up. And so this energy that's emitted upward ends up, we could say, escaping at the top of the atmosphere. And that's the primary way in which the Earth's cool. The Earth cools to space. And so, because if the Earth didn't cool to space, that sunlight would just heat us up forever and we would boil and not really be here right now. And so we needed a mechanism in order to cool. And so because we have a temperature and we emit energy, we're able to cool and lose that energy to space. And so it's the balance between those two things that determines about the amount of energy coming in versus the amount of energy that we emit out to space and lose to space. That balance determines how much, what our temperature is, what the temperature of the Earth is.
And does that bring in your research on the clouds? Is the clouds what kind of controls how much is released or insulates us from releasing too much?
Yeah, that's right. So if you change clouds, well, clouds in general impact how the energy flows around the planet. So it affects clouds from the considering sunlight. If you have lots of clouds, it actually reflects that sunlight back to space. And so if you're underneath a cloud on a warm, sunny day, it turns out that shade provided by the cloud is cooling, and that's because it makes you feel cooler because it's reflecting that sunlight back to space. Now, from the other perspective, from an energy emissions standpoint, right, back to what we were just talking about, everything has a temperature, emits energy to space. If that cloud comes overhead, then it actually reduces the amount of energy that is lost to space from those emitted wavelengths. We call them long wavelengths, or you can just think of it, call it terrestrial radiation. But so that is reduced when you have a cloud overhead. And the best way to kind of visualize this or to kind of understand that effect is on what I would say a cold winter night. So if you have the coldest winter nights are oftentimes clear conditions, right? And that's because you can lose this energy. It can be emitted by the surface and go directly out to space. But when you have clouds here on that same type of night, clouds provide an insulating effect and help to keep that energy in and raise your surface temperature. So it's these two effects of clouds, both the warming effect by helping to reduce the cooling to space, right? Less cooling to space when you have clouds, and the reflection of sunlight to space by clouds. It's the balance of those two effects that gives us this total cloud effect, which is challenging. Is they have these two compensating effects that in a lot of cases can be roughly the same order of magnitude. So it's hard to
Oh.
figure out which is most important in what situations because they're not always the same effect is important at the same time.
And so, how does the sea ice that you study? How does that fall into play then? How does that fit in the picture?
So sea ice is a very interesting a different animal. So if you put clouds over top of sea ice, now there's a whole bunch of other kind of other considerations. But to give a little bit of context, over the last 40 or so years, we've seen a a tremendous amount of decline in Arctic sea ice. And this has been brought about by increased emissions of carbon dioxide, have led to warming temperatures in the Arctic. And those temperatures have warmed by more than twice as fast than the rest of the globe. So when you have these much larger, much faster warming, so to understand how sea ice is really plays into this picture of how clouds are modifying the energy flows around the planet, we can take a historical perspective first, which is over the last 40 years, we've seen a tremendous amount of change in the Arctic sea ice, right? Where we've seen declines in September that are on average of 13% or so per decade. We've lost nearly about 3 million square kilometers of sea ice in that time, which is equivalent to the land area of Alaska, Texas, Montana, and California combined. So to put that into perspective, yeah, it's a lot of sea ice. And you put that into more perspective, because when I looked up that statistic the first time, I didn't actually realize how large Alaska was. Alaska is actually a very large state, 3 times the size of Texas, and so that's roughly that's more than 4 times the land area of Texas that we've lost in terms of sea ice. So it's dramatic declines, and so these declines in sea ice have been shown through a lot of different studies, have been our direct response to the increase in carbon dioxide in the atmosphere, which is warming the planet, but this warming isn't distributed equally across the planet. It's more than the Arctic itself is warming more than twice as fast as the rest of the planet. And in fact, areas of the Arctic are warming 3 and 4 times faster. Certain regions of the Arctic are. And so this warming in temperature is what's giving us this large decline in sea ice. So a real key question here in terms of sea ice and how it's going to change is what are clouds doing over top of it. So for a long time, I'm going to say more than 30 years, there's been a hypothesis out there for clouds and how they may respond to sea ice. And so stepping back again for a second, you could think of clouds as an engine, sort of, where their fuel is water vapor. So if you have more water vapor, you tend to have more clouds. It's not exactly that simple. There's a lot of other things at play, but for first order, it's a pretty good relationship between water vapor. A moister atmosphere is a cloudier atmosphere, essentially. And so in the Arctic, if you're uncovering all of this, if you're melting back all the sea ice, you're uncovering a lot of the Arctic Ocean underneath. And so the hypothesis was, well, if you uncover more of the Arctic Ocean, now you can actually evaporate more of that water, moisten up the Arctic atmosphere, and that is then going to lead to increased cloud formation. And so as I mentioned before, if you increase clouds, they have these two effects. But in summertime, the primary effect, because the sun is up, the primary effect is actually this cooling effect, the shading effect of clouds by reflecting sunlight back to space. So from the situation, not exactly hypothetical, it's actually going on. So from the situation, what happens is you melt back the sea ice, you increase the evaporation from the surface, and then you potentially increase cloud formation, and then that clouds would reflect more sunlight to space and help kind of slow down the rate of sea ice loss, right? And so that's the hypothesis that we had for 30 years, but it wasn't until recently, with the launch and the long data record of NASA's CALIPSO and CloudSat instruments, that we were able to really get data on it and understand, is that hypothesized interaction between clouds and sea ice actually happening? Are clouds helping to slow down Arctic sea ice loss? And so we looked at that, and what we found from the CALIPSO CloudSat data is that actually isn't happening. And that hypothesis that we were thinking all these years isn't really the way the real system has unfolded anyway over the last decade. So that's the primary way in which clouds, that we've been thinking about Arctic clouds and how they influence sea ice. A long answer to that question, but
no, but I like that. The fact that you talk about, the scientific community kind of thought, okay, this is how it's going to work. But that's when we got enough data, we realized, okay, it's really not working that way. And that's perfect. Kids sometimes don't realize that our understanding of things change as we develop more, get more data and understand more about it. So water
That's why we
simulation.
need the data. Why
That's
we need
why
the
we need
data.
the data. That's right.
Well, I want to ask, so how do you go about collecting data, and what sorts of instruments are you using to collect that data?
So there's a lot of different instruments that are out there collecting different data, and how I like to explain it, if you look at all of NASA's different satellites that we have in orbit, we have more than 20 different satellites that we're operating at any given time, really. And that number of satellites, you might think, wow, that's a large number. But as we talked about before, the climate system is like a big puzzle with all those different pieces: oceans, atmospheres, plants, animals, ice, all these things. And so not any single instrument is really perfect for all of those different needs, right? All of those different variables that we need to understand in order to figure out how our system's evolving and changing. And so what that leads us to is a lot of different instruments for different purposes, right? The right tool for the right job kind of thing. And so over the last 30 years, we've had observations from space, primarily, and being from NASA, I primarily use space-based observations, but we've had some observations of the energy that's been emitted from the Arctic over the last 30 or so years. The problem is that there are lots of difficulties with turning those observations into kind of cloud properties. So there are a lot of models that are involved in trying to interpret the energy that we see in space and what it actually translates to in terms of temperature, humidity, and cloud properties, cloud characteristics. And so using what we call, the jargony term is thermal emission, but that's just, the energy that is emitted by the atmosphere and the land and the clouds because it has a temperature, like we were talking about before. But using the kind of energy, the measurements of that energy, we can make some, I'll say, educated guesses of what the cloud properties are. But it turns out that because the Arctic has a sea ice surface, it's a very complicated surface that is highly variable, right? You think of sea ice and you see pictures of ice covered in snow and it looks very homogeneous. But when in actuality, when you get into a lot of the times, the wind blows that snow around this. You actually have a very rough surface. It's not very even. And in summertime, when you have melt happening, you get, certain areas melt faster than others, and so you have snow in some places, you have bare ice in other places, which have different characteristics and look different from space. And then you also have what we call melt ponds on sea ice, which are, places where this ice has started to melt, but not enough to fall through. And so you have these lakes essentially at varying sizes, but you have these ponds and lake-size bodies of water on top of the sea ice, and all these different characteristics of the surface make it really hard to interpret what you're looking at from space. So we had those measurements for about 30 years in the Arctic, but because they're hard to interpret, we couldn't really say anything definitive about how the clouds were changing. What the data that really allowed us to kind of make this new advance and this new understanding of how clouds are actually not responding to sea ice melt in summertime was because of the CloudSat and CALIPSO, excuse me, NASA CloudSat and CALIPSO instruments. And so they were very different from before, from the other instruments I was talking about. CloudSat is a radar in space. So it's just like if you turn on the news in the morning and you see the precipitation radar and you see where the rain is in the area. Essentially, that's what CloudSat is, except it's up in orbit pointing down. And so it can profile the atmosphere and tell you where clouds are very accurately in height and where precipitation is very accurately in height, whether it's high up in the atmosphere, 10 kilometers, or whether it's closer to the surface, like 1 kilometer or lower. CALIPSO is a LiDAR, so it's like a radar, except it uses light, shorter wavelengths. It's actually a green LiDAR, CALIPSO is. And so because of the smaller wavelength, it actually is much more sensitive to the things in the atmospheric constituents. And so it can look at thin clouds, because if you look up at the sky, right, clouds sometimes are really thick, sometimes they're very thin. And so these different technologies, different instruments have different strengths and weaknesses. The radar is able to penetrate thick clouds and look at precipitation, whereas the LiDAR is not able to penetrate those clouds, but is much more sensitive to thin clouds. So the key advance, though, from these, what we call active, so these are active instruments, so they're actually putting out pulses of energy instead of just observing what's being emitted from the Earth underneath. So these active instruments provide us a very fine detail of what the vertical structure of the clouds is, where are the clouds in height, and they can detect them very accurately. And so those measurements were really critical in advancing our understanding of these clouds, because the previous measurements were just, there was too much uncertainty in those data in order to say anything too definitive about how clouds were changing the sea ice.
I really like that you bring up uncertainty in measurements, because I think that's something it's difficult to explain, I think, or difficult for students at first when they start taking measurements. They're used to like a ruler maybe, and so they can take a measurement there. But I think it's important to understand that there is uncertainty with different measuring devices, and that like you're saying, the LiDAR and the is it CALIPSO? Is that the LiDAR?
CALIPSO, yep. CALIPSO is the LiDAR. And that one's here, the science team's here at NASA Langley for that one.
Okay. So it's true that because they're more active and they're putting out those pulses, that increases the certainty then of the measurements.
Yes, because we know what the pulse is, right? We know how much energy we sent out, and so we know that when we send it out and it bounces back, we know how much we sent out. So we have, well, the term is the boundary condition. I can't think of a better word for it right now, but we know the initial amount of energy, and so that we can accurately know the change. But when you're just observing the energy that's coming to you, you don't know what the kind of initial state was, what was the emitted amount. So you have to use other data sources to give you kind of an idea of what those conditions are, so that you can then interpret what the energy that you're receiving in space better, right? If you don't have that type of information, it makes it really hard to understand what you're seeing. Because, for instance, if you had the same cloud, it was the same kind of characteristics, but you changed the temperature of the atmosphere around the cloud, or above and below the cloud, the energy that we see from space would be different. So the cloud is the same, but the temperature around it has changed, and so that interpretation is challenging if you don't know that other information. So the active sensors, we have that information, and so it makes it much better. And it also provides us the vertical profile, much finer vertical information, or where the clouds are in height, than you get from the thermal imagery.
Well, you mentioned. Let me ask you kind of a generic question. I could hear already people asking and listening to this.
Yeah.
Is you say that in areas of the Arctic, it's the climate change is changing. I mean, up to 3 times faster even than the global average, right? And when I think of climate change, it's like, all right, so we don't drive as much, and so our factories don't put out as much, and that's what changes. People aren't driving in the Arctic, and there's no factories there, and so how are people really impacting the Arctic if they're not there?
Okay, that's a great question, and so this is something that I would say one of the biggest things that I've learned in my 15-year journey so far through science is that we live on an interconnected planet. And our planet is interconnected by our oceans and the global ocean currents, by our global atmosphere circulations, where the winds are really carrying, in the US, we know the winds from Africa are carrying Saharan dust to the US East Coast. We see that. The storms in the mid latitudes are carrying air from that we have, our emissions, our pollution, and that mixes in with the air. It's being carried into the Arctic. And so, as I mentioned before, global climate change is really primarily driven by the increased carbon dioxide emissions, which get into the atmosphere, and those are happening globally. But because we have these atmospheric circulation patterns, so sorry, let me step back. When I say atmospheric circulation patterns, I really just mean wind. So in the atmosphere that are that are moving the air all around and taking air from here to there, right? From the US East Coast towards Europe, and from Europe into the Arctic, or from Asia into the Arctic, right? So these winds are just mixing all of the air all around the planet at any given, all the time. And so, the emissions that happen today, within a few weeks, they're going to be distributed around the whole planet. So we think of carbon dioxide as what we call a well-mixed gas, which means there are variations from one place to the other, but in general, the concentration, the amount of CO2 in the atmosphere is pretty homogeneous across the planet, and gets mixed pretty quickly over the course of several weeks. That's how we're impacting the Arctic, is that, the changes here are the winds are connecting our entire planet, making the Arctic feel the changes, or our impacts. Our actions are impacting the Arctic.
That's perfect. And that's one thing a lot of people don't realize, is that how big the impact is that we have in other places, how interconnected the world is. That might be my favorite quote right there. When I say atmospheric circulation, I'm talking about wind. That might be my favorite quote now. I like that.
That's all it is. Yeah.
We get into our jargon and use it, but then we know there's always a simpler way of explaining it sometimes. And so I like to throw that out to, hey, we're talking about wind. Okay. I love that. All right. I know that you're not studying that, but I don't know if you happen to know by chance, with the whole global shutdown due to the pandemic.
Yeah.
Is there enough data yet that people can start to see change in like the amount of clouds or anything like that, or is there just not enough data yet to see that? Or
So when it comes to, I've looked at this and have some colleagues that are looking at this in more detail. And so from there are a lot of different aspects. I guess this just should be one of the themes of this, is that nothing is as simple as it seems. Everything is more complicated. And that's what we're learning every day, right? We have this interconnected system of all these moving parts: oceans, atmospheres, ice, all these things. And so from a cloud perspective, there's a couple ways we can approach what's happening with the lockdown in response to COVID-19. The first, and actually is something that's definitely observable, is the reduced number of contrails because of the reduced number of air traffic, right? So you have airplanes high in the atmosphere, they make condensation trails or contrails because of their exhaust. And so there are fewer of those in the atmosphere because there are, well, the statistic I looked up yesterday was that, pre-COVID-19 lockdown here in the US, there was something like 485 flights per day between US and Europe, and now we're down to like 95. And so there's a lot fewer planes in the atmosphere. And in fact, it's about 20% fewer emissions of carbon dioxide are coming from the airplanes right now. And so that's a good thing that we have these reductions in emissions. And so there's that aspect that we can see. But one of the most critical and puzzling and important questions with clouds is, how are clouds responding to changes in aerosols? So when I say aerosols, those are little particles in the atmosphere that can come from pollution, right? They can come from dust. They can be germs, actually. Viruses and bacteria can serve as aerosols. And these little particles in the atmosphere serve as what we call condensation nuclei. Those are places where water vapor can condense and form droplets. Without these condensation nuclei, these little surfaces that the water can condense on, without them, it would be much harder to form clouds, actually. So they're a very important part of the system of clouds and how they evolve. So the question is, how do the number of these things in the atmosphere, how does the number of cloud condensation nuclei influence the cloud properties? We have some hypotheses, and we have some kind of things that have been demonstrated with observations, such as if you have more of these cloud condensation nuclei, you end up with more smaller droplets in the clouds. That's important to know, because if you have more smaller droplets, that cloud actually is reflects more sunlight to space. So there's this interesting connection between, the number of droplets in a cloud and their sizes and how it interacts with sunlight. That could be very important. And so that's a big question when it comes to climate change as well, because in addition to the emissions of CO2 that we've done over the last more than 100 years, human activities also contribute to an increased amount of aerosol particles through our activities put more dust and more pollution and all kinds of more soot, all kinds of different particles in the atmosphere that weren't there before. And so those types of particles have the ability to affect clouds. And so with the large reductions in emissions right now and pollution, right? There's a study from using a NASA data OMI, the OMI instrument, which is an air pollution instrument, ozone monitoring instrument. It showed that there's about a 30% reduction in pollution over the last several months along the I-95 corridor here on the east coast of the U.S. So we've seen dramatic reductions in air pollution, right? And so the question is, are those changes in pollution and aerosols in the atmosphere affecting the clouds? So for that, we need some really detailed studies, and NASA is funding some of those, but it's too early to tell if that's going to if we're going to be able to what we're going to be learned from that. It's just too early to tell.
Fair enough. Fair enough. I was guessing that was the case, but I know people yell at us if we don't ask.
No, this is a very it's a rare kind of opportunity, an experiment where like you shut everything off, right? Who thought like before 2 months ago that we would have that we would be able to, as a society, to all of a sudden stop everything, not almost everything, on like a dime. And then so this is a very interesting opportunity, kind of an experiment to see, well, what happens when all of a sudden pollution drops by 30%. Right? And what happens to the atmosphere and the temperatures and the clouds, and so what can we learn from that? So it's an exciting opportunity. It's like a silver lining from this very great cloud.
But thank you for explaining that. Thank you for discussing all the cool research that you're doing, and
No problem. Happy to do it.
Things for us. We appreciate your time.
Thank you for listening to our podcast. Please hit the subscribe button so you'll continue to hear about new and exciting STEM-related work being done.
Tweet us questions, suggestions, and requests at Purdue SOS or email us at k12science@purdue.edu.
Until next time, be super, and remember, you are someone's hero. Boiler up!
Hammer down!